Welcome back to my stream. Excited to be here, and let's see where we left off. Where did we leave off our intrepid hero? Right, we were working on trying to get the chunk to be part of source, right? Oh, right, part of the compiler. And let me just make sure my sound is up here. I keep messing that up. Okay. Hopefully that sounds good. Yesterday's sound was, or last stream's sound was kind of bad. Okay, so let's see. Compiler, there we go. And we were trying to put the chunk into the compiler, and we were running into problems. And I do have ref cell for, oh, had error in panic mode, right? So, and I think, so the last suggestion that I got from chat was to put it in, wrap it in a RC ref cell. So I'm going to do that. So right, what I'm trying to do, right, is get this error. Where is it? Where do we report the error? Oh, it was in VM, maybe? Okay, let's undo this change. Source VM. Yeah, we were putting chunk in here, right? Because we wanted to be able to report a runtime error without having to pass the chunk in. And the reason for that is because we were calling binary op, and binary op doesn't have access to chunk, but it does have access to self. So if we can put the chunk into self, then we can have it accessible to the error routine. So we're going to use our standard RC and standard cell, no, ref cell, yep, and then put that here, chunk. It's going to be RC ref cell chunk, just like that, with the correct syntax. There we go. And then we'd have to create a new one, I guess. RC new ref cell. It's kind of ugly. New chunk. New, right? And then set it here. Self chunk is equal to chunk. Except we have to RC new ref cell new chunk. And then we can be able to call self run without passing the chunk in. This becomes mut self. And then every place we have chunk, we have to say self.chunk.borrow. This just needs a borrow, not a borrow mute, right? Where else do we need it? We don't need it in read byte because it's going to be passed into self. We don't need it in read constant, and we don't need it in runtime error, right? There we go. So read byte doesn't need it. And here we just say self chunk, oops, borrow like that. And here it's self chunk. Here we're reading, so we don't need. Here's a get. And this doesn't need it now. And now we can do self chunk borrow to get the line. Oh, wait a minute. So if we're just borrowing it, let's see if this compiles first. It does not. Oh, we don't need chunk free anymore. I'm going to blow that away. And then let's open up chunk and blow away the chunk free. There's no reason to do it, right? Because we drop, Rust does the free for us. We allocate the chunk here and then it gets dropped. Well, not really, because it gets put in here, but when the VM interprets the next thing, then we overwrite the old one and then it gets dropped. Okay. So what are the warnings? Boolean is not used, nil is not used, and free and value is not used anymore. So we can blow away that as well. Value. And free. So we don't need that. Epic says blowing chunk sounds like vomiting violently. Yeah, it actually is a expression for that. And we don't need free for VM. Let's blow that away too. Which means we don't need it here. Okay, so I think we have some decent cleanup. The 3 warnings are just we're not using Boolean and we're not using nil, right? So I think that's all we had to do. I think Epic, that was your suggestion yesterday, or sorry, 2 days ago. I didn't stream yesterday. To just wrap it in RC like this. And I was trying to put ampersands and stuff like that in there, and then messing around with lifetimes, and it just wasn't working. But this works. However, I did notice as I was going through this, we're not doing a borrow mute anywhere. So if that's the case, we don't actually need the ref cell. Let's try it without the ref cell. Now that we have this working, let's mess it all up. Which means we don't need the borrows. Okay, does that compile? Nope. Of course. Oh. And we don't need the ref cell here. Okay, that builds. Does it run? Cargo run. What was my standard test? 3 plus 4 times 5? 23? That's correct. Okay, so we're good. Yeah, if we need mutability, right. Epic says the RC ref cell suggestion was based on the assumption you needed mutability. And we may do in the future. I don't know what's coming. So we know the solution to that. If we need it, we can just throw it in a ref cell at that point. Most of these things do take mut self though. Oh, right, but we need to be able to mutate the chunk itself. So, all right. So when that happens, we'll make the change. But for now, it looks like we can get away without it. And that means now, okay, maybe I should make this separate. A separate commit, right? Because we did a bunch of cleanup and we put the chunk into a ref cell. An RC. So let's make this a separate commit. Cargo Clippy. Oh, we got a little cleanup. Oh, right, the matches thing. I noted that on Togglebit's Discord. Oops. Where is it? I got the wrong line number. Here it is. So we can just say if. We can just return matches. Bang. Self value number. The capital V. Yep. Okay, so that cleans up that one. We have an unnecessary let binding on line 20, 29, 30. Oh, right, because we were doing a free. And now I took away the free. We don't need that anymore. Okay. That's good. And then what else is it complaining about? The Boolean and nil. That's it. Okay, so that's all cleaned up. Git add source, git commit, move chunk into an RC for error reporting purposes. Okay, so now we're going to finally do the binary op error checking here. Right, so we're basically doing this part of the macro now. If is number peak 0 and not is number peak 1, then we're going to return a runtime error, and that's where we got stuck because we needed to pass in the chunk, and now we no longer do. So the error message is operands must be numbers. And that that already returns a runtime error. So we're all good there. So then we're able to pop them and know that the binary op will work. And I think in a value right now, if we don't, we will get a panic if we try to add, subtract, multiply, or divide non-numbers. So if there's a bug in our code that causes that to happen, that's done. And of course, this doesn't work because, I have to okay it. I have to, it's got to be result. And then I do have to okay down here. And then just make sure that this results in a result. Ooh, okay, so that means our arms are going to be bad, right? So we have to okay all of these guys. Oh, no, we don't. We can question mark these guys. Question mark, there. Yeah, okay, good. All right, so that's this part. Yeah, I realize it's a monster of a macro. Well, in Rust, we're just making it a regular function. It's not what I'd normally consider good C practice, but let's roll with it. The changes are similar to what we did for unary negate. First, we check that the two operands are both numbers. If either isn't, we report a runtime error and yank the ejection seat lever. If the operands are fine, we pop them both and unwrap them. Then we apply the given operator, wrap the result, and push it back on the stack. Right, so that's what we're doing here. Note that we don't wrap the result by directly using number val. Instead, the wrapper to use is passed as a macro parameter. Is that this? Oh, I see. Yeah. Okay. So we're doing all of this up here. All of these got converted into these little tiny closures. Soon I'll show you why we made wrapping the macro an argument. So maybe this closure won't work. Let's find out. 2 new types. All of our existing CLOX code is back in working order. Finally, it's time to add some new types. We've got a running numeric calculator now that does a number of pointless paranoid runtime checks. We can represent other types internally, but there's no way for our users program to ever create a value of one of those types, right? We can't, if I say cargo run, I can't say 3 plus true, 3 plus true, because it won't parse, yeah. Not until now, that is. We'll start by adding compiler support for the 3 new literals, true, false, and nil. They're all pretty simple, so I'll do all 3 in a single batch. I'm not kidding about dedicated operations for certain constant values being faster. A bytecode VM spends much of its execution time reading and decoding instructions. The fewer, simpler instructions you need for a given piece of behavior, the faster it goes. Short instructions dedicated to common operations are classic optimization. For example, the Java bytecode instruction set has dedicated instructions for loading 0.0, 1.0, and 2.0 and the integer values from -1 through 5. This ends up being a vestigial optimization given most mature JVMs now JIT compile the bytecode and machine code before execution anyway. All right. With number literals, we had to deal with the fact that there are billions of possible numeric values. We attended to that by storing the literal's value in the chunks constant table and emitting a bytecode instruction that simply loaded that constant. We could do the same thing for the new types. We'd store, say, true in the constant table and use an op constant to read it out. But given that there are literally Only 3 possible values we need to worry about with these new types. It's gratuitous and slow to waste a 2-byte instruction and a constant table entry on them. Instead, we'll define 3 dedicated instructions to push each of these literals on the stack. All right. So let's go. Oh, are we clean? Are we good here? Git add source, git commit -m. And this was just binary arithmetic operators. It was section 18.3.2. There. Okay. So we're going to add these opcodes here in chunk. They're putting them between constant and add. I have to return a negate in here. I guess it, oh, it was going to be, all right. I don't care where they go. We'll call this nil, true, and false. Doesn't matter. Our scanner already treats true, false, and nil as keywords, so we can skip right to the parser. With our table-based Pratt parser, we just need to slot parser functions into the rows associated with those keyword token types. We'll use the same function in all 3 slots, just literal, literal, and null and prec none. Okay, and that comes. Where do we generate that table? Is that in VM? I've already forgotten. No, the rules aren't there. It's in the compiler. Oh, it says it right here, compiler. Okay. So all we do here is rules token type, and this is false as usize. Our prefix is going to be some CC literal. Infix is none, and then precedence is precedence none. I wonder if I could just modify the parse rule directly. Can I do that? Can I say dot prefix here is equal to some, can I do this? Let's find out if this works. Oh, I forgot that, or I deleted it. And we don't have literal yet, but if that works, then we can clean these guys all up, right? Prefix equals like that. Yeah. Okay. And then, oh, this has 2 changes. So I guess we can just leave those alone. Those have 2 changes. This one just has 1 change. So we can do this. All right. So we have that guy here, and then we have minus, plus, slash, star, number, and then false and true and nil are all going to be the same. Right, and we don't have literal yet, so we're about to write literal. When the parser encounters false, true, nil, or true in a prefix position, it calls this new parser function. I'm saying put it after binary, sure. So match self.parser.previous.type, and it's going to be token type false is going to be emit, self emit byte, opcode false into comma, and then underscore is going to be unreachable, right? And then we have true and nil. Oh, he has nil and true. Okay, that's fine. Okay. Now does that build? No. What's wrong here? Oh, we don't have, okay, we have to implement the instructions now. That's fine. Is that the only error? This is in our VM. We have to implement them. Okay. Since parse precedence has already consumed the keyword token, all we need to do is output the proper instruction. We figured that out based on the type of token we parsed. On our front end can now compile Boolean and nil literals to bytecode. Moving down the execution pipeline, we reach the interpreter. So I guess we're in the interpreter now. Op constant. I have negate here. Okay, I'm not going to worry about the exact order. Okay, so this just says push nil, push true, and push false. So opcode nil is going to be self stack push value nil. That's all I have to do. Yeah, that's all I have to do, because now it's just complaining about just true and false. Okay. So then this becomes true and false. And this will be Boolean true and Boolean false. Yep, okay, that worked. This is pretty self-explanatory. Each instruction summons the appropriate value and pushes it onto the stack. We shouldn't forget our disassembler either. Well, we can't in Rust. Forget it, I mean. All right, so they're all simple instructions. So we have nil, true, and false. And we're going to just change the divide here to nil, true, and false. Very good. With this in place, we can run this earth-shattering program. True. All right, let's see if this works. It compiles. All our warnings are gone because now we're using Boolean. Cargo new. Oh, sorry. Cargo run. True. Boom. Panic. Oh, because our display. Oh, yeah. So that's one of the things is when we build the, when I hit Control D to do a cargo check, it doesn't actually do any of these, huh? Oh, wait a minute. We are displaying Booleans and numbers. What's it failing on? Line 110 in chunk. Oh, right. We have to translate it back the other way. All right. Which means I have to get the correct order. So 7 is opcode nil. 8 is opcode true. And 9 is opcode false. Forgot about that one. Good thing it just blows right up. True. Perfect. Op return is the compiled version, and then as we execute it, we see a true, and then we get a true out. Nice. Except that when the interpreter tries to print the result, it blows up. We need to extend print value to handle the new types too. Okay, I did that before because Rust wouldn't let me do it without it. I guess I could have ignored it. There we go. Now we have some new types. They just aren't very useful yet. Aside from the literals, you can't really do anything with them. So I say 3 minus true. Oh, look at that. We got the error message. Operands must be numbers. Nice. So that error testing works. Minus true. Operand must be a number. There we go. Oh, there's a period here. Remember, we have to be very exact because our test suite is trying to match this the error message directly. Yeah. So we need a period here. Source, and that's in VM. Okay, there we go. Okay, so that's the end of section 18.4, 2 new types. Oh no, we're still doing it. We're still working our way through it. Logical, not, and falsiness. Okay, so we have 2 new types. Okay, git add source, git commit section 18.4.0 to new types. Okay, so logical not and falsiness. The simplest logical operator is our old exclamatory friend unary not. Print bang true is false. This new operation gets a new instruction. And of course I've forgotten, is it in chunk? Yeah, it's in chunk. So down here we'll add not. Down here we'll add a not. There we go. We can reuse the unary parser function we wrote for our unary negation to compile a not expression. We just need to slot it into the parsing table. And that's in compiler. Yep. So we can just copy this and change that to not, and then just change this to unary. Oh, bang. And now we need our instruction, right? Because I knew we were going to do this, unary function already has a switch on the token type to figure out which bytecode instruction to output. We merely add another case. That's in the compiler. Right. So now we're gonna switch this over to a case. Match operator type. And this will just be minus, means do this. Token type. Not means self emit byte. Opcode not into like that, and then everything else just becomes unimplemented. Like that. Ooh, it doesn't like that. It's bang. I keep forgetting. All right. Okay, so now we're back in the chunk. That's it for the front end. Let's head over to the VM and conjure this instruction into life. Let us do exactly that. Where's negate here? So I'll put it right here between. All right. I guess these four should be up here. I guess it doesn't really matter. Okay, opcode not becomes push bool val is falsy pop. So we'll first have to say let value equals self pop, and then we're going to say push bool val is falsy. Self stack push self. Oh, can we make that on the value itself? You can say value is falsy. That might be the best way to do it. And it's going to be a Boolean. Value Boolean. Like that. Right? And we just have to write is falsy. Like our previous unary operator, it pops one operand, performs the operation, and pushes the result. And as we did there, we have to worry about dynamic typing. Taking the logical not of true is easy, but there's nothing preventing an unruly programmer from writing something like this, print bang nil. For unary minus, we made it an error to negate anything that isn't a number. But LOX, like most scripting languages, is more permissive when it comes to bang and other contexts where a Boolean is expected. The rule for how other types are handled is called falsiness, and we implement it here. So I'm going to... It seems like it would belong in the value type itself. So I'm going to put it there, and then if things blow up later, we'll have to fix it value. So we can just put here, we have is number already for it. So we can say pub fun is falsy. Self returns a bool. Right. And I was thinking, well, I should use matches again, right? But is bool value and as bool value. So we can say matches, right? Self with value nil or value Boolean false, right? And that's is falsy. Locks follows Ruby in that nil and false are falsy and every other value behaves like true. We've got a new instruction we can generate, so we also need to be able to ungenerate it in the disassembler. All right. I'm just going to put it at the end. Opcode not is a simple instruction. Op not offset, just like that. Okay. So that's 18.4.1. Can we do it? Cargo run. Not false is true. Not true is false. Not 5 is false. Not nil is true. Okay. That's working. Clippy's happy. Git add source. Git commit -m section 18.4.1, and it was called logical not and falsiness. Very good. This is going very well. Equality and comparison operators. That wasn't too bad. Let's keep the momentum going and knock out the equality and comparison operators too. So this is a sign. This is not equal. No, that's not a sign. That's equals in our version of it. Okay. That covers all the operators that return Boolean results except the logical operators and or. Since those need to short circuit, basically do a little control flow, we aren't ready for them yet. So here's the new instructions. So we're going to add equal, greater, and less. Wait, only 3? What about bang equal? Listen, we could create instructions for those too. Honestly, the VM would execute faster if we did, so we should do that if the goal is performance. But my main goal is to teach you about bytecode compilers. I want you to start internalizing the idea that the bytecode instructions don't need to closely follow the user source code. Okay, so we'll just add these guys here. This is a greater and less. Right, so we can just compare it both, right? The VM has total freedom to use whatever instruction set and code sequences it wants as long as they have the right user visible behavior. Is A less than or equal to B always the same as not A is greater than B? According to IEEE 754, all comparison operators return false when an operator is nan. That means nan is less than or equal to 1 is false, and nan is greater than 1 is also false. But our desugaring assumes the latter is always a negation of the former. For the book, we won't get hung up on this, but these kinds of details will matter in your real language implementations. All right, the expression A bang equals B has the same semantics as bang open paren A equals B close paren. So the compiler is free to compile the former as if it were the latter. Instead of a dedicated op not equal instruction, it can output an op equal followed by an op not. Likewise, A is less than or equal to B is the same as bang open paren A is greater than B close paren. And A is greater than or equal to B is bang open paren A is less than B close paren. Thus, we only need 3 new instructions. Over in the parser, we do have 6 new operators to slot into the parse table. All right, so he means compiler, right? Where is the? Here it is. And these are all binary with prec. Oh, we have prec equality, prec comparison. And I call this token equals, I think. So we can say rules, token type equals as use size equals parse rule Prefix is none. Infix is binary. And then precedence is precedence equality. Right? Does that work? Oops. Yeah, okay. And then we have greater, greater, equal, less, less equal, and all of those are identical. Does parse rule implement copy? It does. So I could just copy those, right? I can say rules token type greater as usize is equal to this parse rule, which is similar to this guy, except we're going to use comparison. And then, oh, I misspelled that. And then can I do this? Greater, equal, less, and less equal. And just copy the parse rule from greater. Rules token type greater as usize. Yeah. Yeah, I didn't mind that at all. Okay. Remaining 5 operators a little further down on the table. Oh, I forgot the bang equal. Okay. Bang equal has the same as equal equal. Okay. So we can say rules. We can just do this. Rules token type equals as usize equals that. Okay, it's a little messy, but there it is. All right, and then in our compiler, no, this is in chunk. This is the disassembler. I guess, our compiler for emitting bytes, oh, this is just for operator type in binary. Okay. Yeah, it doesn't do full checking there, so binary. I mean, it doesn't, I just have a to do here, so it covers all the other cases. All right, so we have all of these token types. Token type bang equal is self emit byte opcode equal. Oh, look at that, emit bytes with an S into. Do we have emit bytes? Did I do that one? I did. Oh, and I made the first one an opcode and the second one not an opcode, or a U8. So I don't need to into the first one. Opcode not into. That's a little awkward, isn't it? And then we have equals, greater, greater, equal, less, and less equal. Okay. Equals greater, greater, equal, less, and less equal. And these guys just have emit byte like that, and this becomes equal like that with a comma. That's emit byte, and this is greater. Okay, and then we have greater equal, which is going to be less and not. We have less, which is going to be just less on its own. Like that. And then we have less equal, which is going to be greater and not. Okay. Nope. Oh, all of my emit bytes have to be intos. That's right. Okay, very good. The double equal, less than, and greater than operators output a single instruction. The others output a pair of instructions, one to evaluate the inverse operation and the not to flip the result. 6 operators for the price of 3 instructions. That means over in the VM, our job is simpler. Equality is the most general operation. So we can just say opcode op equal. We pop the values and then compare them. Values equal. And I'm just trying to think of how we want to do that. Do we want to implement EQ for... Yeah, maybe. Why don't we do that? Self. I guess we have to pop them first, right? Let A or B equals self pop. Let A equals self pop. And then we say self dot push, stack push. A equals B. Right? I think that's all we have to do, and then we have to implement EQ for value, right? Binary blah blah can't be applied because we don't have partial equal. All right, so let's go over to value and see if we can derive partial equal. Still doesn't like it because, oh right, it has to be a value Boolean. Wow, it was smart enough to say, oh yeah, you're doing a Boolean, you should probably wrap it into the Boolean value thing because that's the thing that has the Boolean in it. That's impressive. That's impressive. Wow. Whoever did that, I'm impressed. Okay, so you can evaluate equality on any pair of objects, even objects of different types. There's enough complexity that it makes sense to shunt that logic over to a separate function. That function always returns a C bool, so we can safely wrap the result in a bool val. Function relates to value, so it lives over in the value module. Right, so I probably should do it this way because we want val nil to return true. But right now, yeah, I mean, I could implement EQ, right? I can implement partial EQ and then get this exact behavior, and maybe that's what we need to do. Let's get this to compile and build first, and then we'll check. Okay, so now they're talking about how to compare it in C because you have this union that you're dealing with, right? First, we check the types. If the values have different types, they're definitely not equal. Otherwise, we unwrap the two values and compare them directly. So as bool, or as number. Given how similar our cases are, you might wonder why we can't simply mem compare the two value structs and be done with it. The problem is that because of padding in different sized union fields, a value contains unused bits. C gives no guarantee about what's in those, so it's possible that two equal values actually differ in memory that isn't used. This has the feeling of, oh, he tried to just ignore all of this and just do a mem compare directly initially, and then it wasn't working, and then he realized, oh, look at that. There's some garbage. Some languages have implicit conversions where values of different types may be considered equal if one can be converted into the other's type. For example, the number 0 is equivalent to the string 0 in JavaScript. This looseness was a large enough source of pain that JS added a separate strict equality operator, triple equals. PHP considers the strings 1 and 0, 1 to be equivalent because both can be converted into equivalent numbers, though the ultimate reason is because PHP was designed by a Lovecraftian eldritch god to destroy the mind. He's not wrong. Most dynamically typed languages that have separate integer and floating point number types consider values of different number types equal if the numeric values are the same. So, say 1.0 is equal to 1, even though that seemingly innocuous convenience can bite the unwary. All right. Oh, yeah, look at that. You wouldn't believe how much pain I went through before learning this fact. Yeah. Like I said, it's okay. Anyway, as we add more types to clocks, this function will grow new cases. For now, these 3 are sufficient. The other comparison operators are easy since they only work on numbers. So we're just doing less than or equal. Less than or greater than. So let's go back. Where was it? In the VM, right? Yeah. So we can say op code greater becomes self binary op a comma b. A is greater than b, and then copy paste and put less. A is less than b. And it doesn't like that because we don't have partial ORed. I wonder if deriving partial... I mean, we can try it. Will that allow us to compare numbers correctly, though? No, it still doesn't like it. Oh. Oh. No, I just want to run the closure. I don't want to compare. Okay, so we can't do partial ORed here. We actually have to implement partial ORed for numbers. Epic Blog says, every lesson learned the hard way should be a lesson spoken about in public because others will run into it eventually. Yeah. Yeah, and that's exactly why he put it in here, right? I guess the only problem is trying to find those lessons learned the hard way. Okay, so we're going to say impl partial ORed for value. And then let's let Rust tell us what we need to implement. Partial compare. Okay. So that's that, right? Oh, I left this in here. I need the type, right? It's still not letting me do it. It let me, so I implemented add for value and then said, okay, well, you can just do that. Maybe because this isn't compiling yet. Value. Yeah. Oh, expected enum value. Oh. No, it's right. It's right that we do need to wrap it in a value like that. Okay. Because it's a but we don't have to wrap this in a value because this returns a Boolean. Got it. Okay. Not a value. That's too many, right? Yeah. Okay. All right. Which means we probably can get away with the partial ORed, right? On value. Let's find out. Yeah. Okay. And so the only thing left now is the disassembler. And they're all simple instructions. 1, 2, 3. Equal. Greater. And less. Equal. Greater. Less. Okay. So now, can I run this and say 3 is less than 4? And it's true. 3 is greater than 4 is false. 3 is less than nil. Operands must be numbers. Okay. Nil is equal to nil. True. Nil is equal to false. False. True is equal to false. False. Did I compare numbers yet? 4 equals 4? True. Good. Okay, so that's all working. And that was section, there it is, 18.4.2. Let's see what Clippy thinks. Git commit, add source, git commit, section 18.4.2, equality and comparison operators. Very nice, very nice. Okay, let's take a look at the challenges. Oh, there's only two. We could reduce our binary operators even further than we did here. Which other instructions can you eliminate, and how would the compiler cope with their absence? Well, can't we implement everything with the NAND instruction, not AND? It just make the code emitting very, very long. Conversely, we can improve the speed of our bytecode VM by adding more specific instructions that correspond to higher level operations. What instructions would you define to speed up the kind of user code we added to support for this chapter? Yeah, the only ones I can think of is adding the specific inequality comparisons, right? Rather than doing these doubles, we can reduce it to a single. What else could you do? I don't know. I don't know. Yeah, I mean, that's the only one I can think of. All right, let's move on to strings. All right, our little VM can represent three types of values right now: numbers, booleans, and nil. Those types have two important things in common. They're immutable and they're small. Numbers are the largest, and they still fit into two 64-bit words. That's small enough price that we can afford to pay it for all values, even booleans and nils, which don't need that much space. Strings, unfortunately, are not so petite. There's no maximum length for a string. Even if we were to artificially cap it at some contrived limit like 255 characters, that's still too much memory to spend on every single value. UCD Pascal, one of the first implementations of Pascal, had this exact limit. Instead of using a terminating null byte to indicate the end of a string like C, Pascal strings started with a length value. Since USCD only uses a single byte to store the length, strings couldn't be any longer than 255 characters. All right. We need a way to support values whose sizes vary, sometimes greatly. This is exactly what dynamic allocation on the heap is designed for. We can allocate as many bytes as we need. We get back a pointer that we'll use to keep track of the value as it flows through the VM. All right, so this is interesting because in Rust does all of this work for us. Heap and memory management. But here we're going to have to do it, or in the C version, it has to be done manually. And that's not something we need to worry about in in Rust. So I don't know how much of this is going to be applicable to our version of the compiler. Using a heap for larger variable-sized values and the stack for smaller atomic ones leads to a two-level representation. Every LOX value that you can store in a variable or return from an expression will still be a value. So for small fixed-size types like numbers, the payload is stored directly inside the value itself. If the object is larger, its data lives on the heap. Then the value's payload is a pointer to that blob of memory. So I wonder if we should kind of implement this by creating a vec of strings and then store an index, a usize, into that vec. And then we can kind of simulate having to deal with memory allocation and freeing, because we'd have to free entries from the vec or mark them as being unused. And that gives our future garbage collectors something to do. Or we could just ignore it and just stick, because I think all we're talking about, right, is adding a new type here of string. I probably shouldn't call it string, because it'll just take a string. Oh, and then of course then copy clone is not going to work and all that kind of stuff. So maybe we do use size. And of course now we can't do anything about it. But then where do we put this array of strings? Well, let's see where we're going. Let's see where we're going with this. If the object is larger than the small fixed size type, meaning its data lives on the heap. Epic says 256 bytes ought to be enough for everyone's strings. All right, then the value's payload is a pointer to that blob of memory. We'll eventually have a handful of heap allocated types in CLOCs, strings, instances, functions, you get the idea. Each type has its own unique data, but there's also state they all share that our future garbage collector will use to manage their memory. Okay, we'll call this common representation obj. Each LOC's value whose state lives on the heap is an obj. We can thus use a single new value type case to refer to all heap allocated types. Okay, obj. Done. Don't have to worry about strings at all. When a value's type is val obj, the payload is a pointer to the heap memory. So we'll add another case to the union for that. There. We can't display it though. I guess all we can do here, value obj. We can write bang f, and then I don't know how we would print it out. Object of O. Right? And all we can do is print out the object number at that point. As we did with the other value types, we could crank out a couple of helpful macros. Is it an object, as object, and object val? So we have that. It's returning it as an object. We're going to need, maybe this isn't just usize. This is going to be some sort of an object thing that contains data, right? Because right now we don't know what the obj is. He declared it, but he didn't define it anywhere. So we're going to have to get there. Unless that's something got left out somehow. Let me look up. Oh, it's just an empty type for now. And then it gets... Okay. It gets information. All right, we'll get there. We'll get there. And this usize is just going to be a pointer into some sort of an obj array somewhere. Every heap allocated value is an obj, but objs are not all the same. For strings, we need the array of characters. When we get to instances, they will need data fields. A function object will need a chunk of bytecode. How do we handle different payloads and sizes? We can't use another union like we did for values since the sizes are all over the place. No, I don't know how to pronounce objs either. Feels like there should be a vowel in there somewhere. Yeah. Instead, we'll use another technique. It's been around for ages to the point that the C specification carves out specific support for it, but I don't know that it has a canonical name. It's an example of type punning, but that term is too broad. In the absence of any better ideas, I call it struct inheritance, because it relies on structs and roughly follows how single inheritance of state works in object-oriented languages. Like a tag union, each object starts with a tag field that identifies what kind of object it is, string, instance, etc. Following that are the payload fields. Instead of a union with cases for each type has its own separate struct. The tricky part is how to treat these structs uniformly, since C has no concept of inheritance or polymorphism. I'll explain that soon. But first, let's get the preliminary stuff out of the way. The name object itself refers to a struct that contains the state shared across all object types. It's sort of like a base class for objects. Because of some cyclic dependencies between values and objects, we declare it in the value module. Okay, so we don't have to worry about that cyclic business here, but we can create an object file here and just create a new pub struct obj. And we're going to create an obj type. O type. I can't call it type. Obj type. And of course we have to define obj type, which is going to be a pub enum obj type. And we're going to start off with string. All right. And then we have to import it in main, right? Can I get away with it here like this? Can I say use object, create object? In order to do that, I need to, yeah, there's no object in the root. I have to put it in main as well. Yeah, okay. So we have the type. Right now it contains only the type tag. Shortly we'll add some other bookkeeping information for memory management. The type enum is this. So it's just the string. Obviously that will be more useful in later chapters after we add more heap allocated types. Since we'll be accessing these tag types frequently, it's worth making a little macro that extracts the object type tag from a given value. We can just grab it directly, right? Oops, didn't mean to do that. Oops. Impl obj pub get type self obj type self o type. Okay, that's our foundation. Now let's build strings on top of it. The payload for strings is defined in a separate struct. Is it now? So we have this obj string, which is this sucker. And I'm going to just use Rust strings. But then where does this obj string go? This definition lives alongside obj. And an object here, a string object contains an array of characters as stored in a separate heap allocated memory. Right, so we don't have to do any of this because we get it for built-in for... Oh, hi, Dayloop. How are you? Sorry, I missed your greeting there. Oh, I see. I see what he's doing, right. So he's defining this obj type, and then every one of these things are going to have an obj at the beginning, and then when we union them all together, the first bit of it is always going to be an obj. This requires programmer... it requires the programmer to be on top of what's going on, right? Because if you have a bunch of different objs things, they all have to start with obj, so that you can extract the type from it, even no matter what type it is. But the compiler doesn't help you. The compiler won't help you with it, which is different to the way other languages work. In C, you have to be disciplined about how you do it, otherwise your program's going to blow up in weird ways. It's going to take forever to debug. Right, so just as a thing, we have struct obj string here, which starts with an obj, right? An obj struct or typedef struct. Something. It contains data and it's called obj, right? And then we have other things in here in length and the chars. I put my start over there, and then we can have another struct like obj data, and it can say obj, and it just maybe has a double range, and I don't know what else would be good to have in here. Long, short, list, something like that, right? You can have whatever, and then we can create a union, right, of string, obj string, and obj data of obj union. And then any one of these things, it doesn't matter what you stick in here because they all start with the obj. So you can cast it. You can say foo equals obj star, whatever. And then you can always say foo dot and any field that's in obj. We had a type in there. It'll work because the first part of the value, the first part of the struct, is always going to be an obj. So you can always access any fields from obj that way. So it's kind of like inheritance. Even though you've allocated an obj string, you can treat it as an obj because it starts with an obj. Anyway, none of that is relevant to Rust because we already have everything built in. obj. Epic says, how are you going to do it in Rust? Rust has union as well. It just requires unsafe to access the members, or are you going to use enums or traits? Yeah, I haven't really thought about it. I was going to go with an enum, actually. Because the enum gives us, all the stuff we need, but it means we don't have to do, if we just stick the string directly in the obj. And that's kind of what we did for the JLox version, right? Is obj type value obj type, right? So now this is going to be fun. What if because we don't need to do any of this. Right? Let's see if we can get away with doing a pub enum obj and just sticking a string in there. So this is all this becomes. Right? And then we have this copy string, which is going to generate an object string, and it's going to shove that value on the stack. But where is it going to put the string, right? We have this copy string, and now it has to allocate. Yep. It has to allocate a string and put it somewhere. So where's that going to go? And in C, of course, the memory is just out there. It's like another one of those global variables. Whereas in our world, it's going to have to be part of the VM, which is going to be a vec of obj, right? I think that's all we can do here in locks, or at least that's what's immediately coming to mind. And you have to use object. Right? And then when we allocate a string, this is in the compiler. The compiler needs to be able to allocate a string. So it's not part of the memory. How's that going to work? Because you can create strings on the fly, right? And then because we have constant strings, but then we're going to also have strings that get created and how is the compiler is going to have to be able to allocate strings in the VM, right? But it doesn't have access to the VM. It's just its own thing. And it can create constants and generate strings internally. But the VM also is going to have to be able to create dynamic strings, right? Because we can add two strings and then push those somewhere. Add two strings meaning concatenate two strings. So what's a good approach for the compiler? I guess we can still create constants in the compiler. where do we put the constants now? They're just, they get added to the chunk. And right now so it's a constants in value array, and as long as the value can store an object, but it's storing an object with a pointer to some piece of data that doesn't exist yet. Right, we're not even using this thing here. Let's take a look again. Object is just this thing. So I could put it here. All right, is that going to blow up? Yeah, see, now we can't do copy clone because it's got a string in there. So I don't want to put it in. And the value array, where's value array? Down here somewhere? Yeah. And it's just a vec of values. So how's this going to work? What's the best way to make this work is to try to, we can continue to store this here, right, as a use size, and then in our value array, we can have a vec of values and then a vec of obj. Oh no, that won't work. Because what I was thinking was, okay, this could be the index into something here, right? Because this doesn't need copy clone. Right? And then, so what we would do, it's kind of awkward, but this obj would be a constant in our value array here, which would have a value inside it that would point inside the object array. And that'll allow us to at least put them into the chunk. Now, I don't know about putting them into the VM yet. So let's get this working. Maybe this will be sufficient. And we just have to write the code correctly here. So in our compiler, we need to add the string thing here. Let's put it here, rules, token, type, string as use size, dot, prefix equals sum c dot string. Like that, and then we have to write string, which is pretty straightforward, string mod self. And then we're just going to pull the string. So we have the previous start plus previous length, and then we can just convert it to a string. And I think, can we just do that using a toString or an asstring or something like that? Let value is equal to parser, previous, lexeme. And oh, do we just have that right there? What is the, I've forgotten what the lexeme is already. Token. I think that's just a string, right? Yeah, it's just a string. So we already have the whole string. But it already has the quotes on it. So I think that's why they do a +1 -2 here to remove the leading and trailing quotation marks. So 1 ... And we can't do -1, right? Rust doesn't do the negatives for indexing from the end, right? So I can say len is equal to parser previous lexeme len -2 1.len. Will this work? String like that, and then let's see if that works. It doesn't like this. Oh, self. Expected string, so it's toString. There, okay. And then we want to create the object. So we say here's emit constant, an obj val. So we're going to create the object value. Self emit object, I guess. Oh, we have to create the object, which is a value. So okay, how are we going to do that? We want to say in our value array, which has got to be part of the compiler, right? No, we have a parser and a scanner. Where's value array used? Do we not use that? What was it, GR? Okay, it's in chunk. Oh, it's called constants. But we're in the compiler right now. Okay, so we have to call into the chunk and say create a new value array. Right, we have get constant, we have add constant, get constant, disassemble. So we have to say create or add object, upfun add object. And the value, we don't have a value yet. Maybe make object? And then we have to have an object, because what I want to have is something and returns an object, value object. Right? I want to say return value object of some number that we just inserted the, what did I just do? We just inserted a new value into this constants value array of an object type. Yeah, how do we create this? This pushes a value, which is fine, but we need the value first. And so we need to generate this new object. So maybe this is make object. Make object self string. And it returns returns an obj, maybe. Does it return an obj, or it returns a usize, which is the index into this object array. So we can say self objects push, or at least we can say let return value is equal to self objects len, and then we want to push a object of types. It's a string, right? String S, right, and then return ret. And that creates the string object. Yeah, this doesn't work, obviously. So we have to do the same thing here. That's awkward. Let index is equal to self constants dot make object string. And then we're going to return a self value object of index. Right. And then here, we need to call the chunk. Yeah, we have chunk in our compiler. So we can say self chunk make object string of value. And it's going to return a usize. And then we can just say self emit constant value obj of constant. Wait. Yeah. Because this returns an object string and it returns the index into there. And then let's just take one more look here at chunk. Make object string returns a value, and this returns a value here. Oh, this returns the value already. Okay, so we just do that. Okay, and what's the warning? Oh, it's never read. Okay, we never read it. That's fine. Is this even going to work? To create the string, we use copy string. Right. Which we don't need to do. There's allocate string. Okay, so we don't need to actually do any of the allocation here. Can we? What will this do? It does say object 0, but it's printing object 0, right? I mean, instead of printing the actual string, it's just saying, okay, we have object 0. Because when we print the value, right, in our display code, we don't have access to the memory that value of object 0 is referring to. Where is that print statement? Is that in main? Oh no, it's in our VM, right? At the end. Right here. We print out self pop. And we should say if that's an object value, then we should pull it out of the constants and print that, right? And how are we going to handle it here? I guess is the question, because eventually you're going to have to be able to print it, right? So this is a copy string allocating memory for the copy. It's using memcopy to copy over the characters. It's sticking a null at the end. And we have to terminate the string ourselves because there is no termination here, right? This is doing is stripping out the quotes, but there's no null at the end of that. It's just a bunch of strings. Sorry, it's just a bunch of characters that we get the length for. Here's our allocation. So we're allocating on the heap. Why can't obstring just point back to the original characters in the source string? Some object strings will be created dynamically at runtime as a result of string operations like concatenation, right? Those strings obviously need to dynamically allocate memory for the characters, which means the string needs to free that memory when it's no longer needed. If we had an ob string for a string literal and tried to free its character array that pointed into the original source code string, bad things would happen, right? So it simplifies the code. We don't have to keep track of whether or not it was allocated. We just assume it was because we allocate everything. So here's how we allocate the string in C. We don't need to do that in Rust. And this is allocating an object, right? So we're creating a new object of type object size, right? And allocates that and returns an object. So, and we still can't print. So here we go. Here we go. So if it's an object, we have to actually print object, and we can't do that yet. We have the data here in C because the value here is just a pointer into memory. Whereas in our version, what I did was I have a pointer into the chunk. So that's unfortunate because, because I would rather have this know about what the string is, right? But the data could either be in the chunk's constants, or it could be dynamically allocated in the VM. And that's not something that's accessible at this point. All we have is the fact that it's in index 0, and we don't even know at that point if it's index 0 in the chunk or if it's index 0 in the VM. So we need a better way to handle this. Like I said, I could just put the string right in here, or the object in here, but the fact that the object contains a string means now copy and clone won't work. Which means, you know, like all of these won't work, because these need to be able to copy the data out. I guess. So I guess what I'm going to do is I'm going to leave things the way they are for now. I'll call this a stream, and I'm going to spend a little time thinking about this, because this is not the right approach for this. Obviously, we need a better approach for storing this global data. Did he get confused with Voila and Viola at one point in his life? Okay. Yes, I did just spend 2 hours drawing a viola to mention that. Okay. So I'm going to, since this is kind of, I mean, this is working to the degree that things can work at all. It's obviously not working because we don't see this, but at least it compiles and it runs. So I need to think about how this is going to happen. So for now, git commit -m started working on strings objects. More work needed. And I'll push this up. And we will call it a stream because I'm not coming up with a good solution right now off the top of my head to figure out how to store these objects so that they're accessible in general. Right? Because right now all we have is they can either be in the VM, right, which I was just calling memory, or they can be in the chunk as part of the value array. And in both cases, oops, don't do that. In both cases, our value does not have any access to that. And I want to be able to say, okay, value needs to be able to print that out, or value needs to be able to access what that object is. And yeah, there's a better solution. I just don't have it. So let's wrap things up. And I will see you tomorrow where we'll actually tackle this and hopefully have a solution for it. All right. Well, thanks everyone for watching, and have a great day or rest of your day. Take care.
Yeah.